Great. So welcome everybody to our Shield webinar. Um, I'm Nick Gross. With me co-hosting is Sandlin Buxner. And our guests today at the Shield webinar are Allison Jaynes and Bill Kurth, talking about, this is part of our ongoing Voyager StoryCorps series, talking about 50 years of Voyager, and their experiences with the Voyager mission, as it approaches its 50-year anniversary. Just a really brief intro to Shield. As many of you know, Shield is interested in our heliosphere, our heliospheric bubble, which is very much like other stars that have astrospheric bubbles, and the interaction between the solar wind and the interstellar medium. I would be remiss if I didn't show you our wonderful movie showing as we fly out from Earth past the sun and the solar wind flowing out through the solar system, interacting with the interstellar medium and all the physical processes that involves, and Shield is trying to understand what this is. And this video shows is the result of a computer model showing that interface, that interaction. Um, oh, Moving on. There we go. Just a couple of other activities on Shield. This is going to be our last webinar for the spring. We're going to come back in the fall with a fall schedule. We're trying to line up some speakers for that right now. We will be contacting some folks. And also we're planning a coffee chat for our graduate students and postdocs that are engaged in the Shield activities and adjacent activities. And we are looking for that to happen in June, just to have them talk about some of the issues that might be affecting them, particularly around some current events that might be of interest. And finally, just wanted to advertise a Shield sponsored but community workshop on the outer heliosphere. So where Shield is involved in is primarily the organizers, but it's for the broader outer heliosphere community workshop in mid-August in Stowe, Vermont, talking about all of the science that's involved in the outer heliosphere, including all of the missions, including Voyager, et cetera, et cetera. So with that as a brief introduction to what we're doing, we're going to turn it over to Allison and Bill, and I'm going to stop sharing my screen.
Thanks, Nick.
There we go. All right. Okay, so Nick, can you hear us okay?
We can hear you just fine.
Okay.
And we can see your slides just fine.
Great. So before we move on from this title slide, it's hard coming up with a title for the Voyager mission. And I think this set of webinars that the SHIELD group has organized is really great. It captures a lot of the history and science that's gone on with the Voyagers. It strikes me that I feel the need to say something about what Voyager means to me and what I think it means to the community. Voyager actually started out as a de-scoped mission. It was called Mariner, Jupiter, Saturn, to explore two of the outer planets. It was de-scoped from something called the Grand Tour, but it actually completed the Grand Tour and paved the way for the realization of just how complex our solar system is by studying not only Jupiter, Saturn, but also Uranus and Neptune. I've had arguments with some of my Cassini cohorts. Every once in a while somebody says, well, what's the greatest mission? And of course my Cassini friends thought, well, Cassini must be. And I said, well, yes, but Cassini wouldn't happen without Voyager. Voyager was a pathfinder for Galileo, Cassini, New Horizons, Juno, JUICE, Clipper, hopefully Uranus orbiter and probe. So it's really opened the outer solar system for study, but it kept going. Not long before Voyager was launched, there were estimates of the size of the heliosphere that were as small as about 5 AU. So Voyager has shown that it's much larger than that. It's explored the boundaries that were only figments of theory and found them to be much different than the theoretical predictions. We're still trying to understand some of those boundaries. And they're now venturing through the stuff between the stars, paving their way for an interstellar probe, also another hope. I think the Voyagers represent humanity's search for knowledge to understand our place in the universe. And some people don't realize it, but when the sun has gone red giant and the Earth is no more than a cold cinder, the Voyagers will be continuing their orbits about the galaxy, perhaps the only sign of an extinct home of an ancient civilization. So, Voyagers, keep going. And Allison, I think, has a great follow-up comment about Voyager and its place in humanity. And let's see if I can go to the next slide here.
Yeah, perfect. Yeah, thanks, Bill. I feel obviously the same as you do about all of this stuff, and super honored to have been part of the Voyager team for the last few years. And I wanted to start with this story of something that happened to me in Japan in August of 2023. So I was at an URSI meeting in Sapporo on the island of Hokkaido, shown there. And after the meeting, as I tend to do, I take a little bit of time to travel in the countries that I visit. And I ended up going into rural Hokkaido just a bit to do some hiking and some exploring. And I was in this tiny town of Bie, which is shown pictured, the train station is pictured on the right there. It's very, very tiny. You would call it a village. It's not even a town. You would call it a village. And it was just like getting off one train and getting onto another, spending a couple hours waiting for that transition. We wandered into a coffee shop in this little village and started talking to a man who could barely speak English. So we were having trouble just sort of telling him what we were up to. But along the conversation, he kind of asked what we did, and we mentioned space science, and he got very excited, and he just started saying Voyager over and over again. And we said, yes, Voyager, exactly. That's part of what we do. And he ran to get a book by one of the inhabitants of the village that had been somehow related to the Voyager mission in one way or another, an astrophysicist who retired in BA and had lived there for many years. And I have a picture on the next slide here of me holding that book that this person had given me to look over. And this man pictured was that individual who was involved somehow tangentially with the Voyager mission, and he was so happy to have met some Americans who had something to do with Voyager. But it's just a testament to the universality of this mission and how it's known in the farthest reaches of the globe, and people are somehow feeling that connection to it. And I really liked having that experience. I just wanted to share it with everyone.
Well, I'll chime in a little bit on that. I often talk to people here in Iowa about what I do. And of course, Van Allen came from Iowa. He started the space sciences here, actually, with Explorer 1. And I can talk about Van Allen, and some people know Van Allen. They've heard of the radiation belts. But I mentioned Voyager, and they all know what Voyager is. So Allison's exactly right that Voyager is a universal symbol of space exploration for not just here in the United States, but across the globe. So let me introduce, both Allison and I work on the PWS instrument. And there's a debate about what PWS stands for. The P is for plasma, and the W is for waves. The Jet Propulsion Lab thinks S stands for subsystem, but I like to call it a science instrument, so This is the Plasma Wave Science Instrument. I should say a little bit about the history because it's somewhat different than the rest of the payload on Voyager. It was not originally selected for Voyager. Fred Scarf from TRW and Don Gurnett from here at the University of Iowa both proposed plasma wave instruments for Voyager, and neither was selected. There's some politics involved that I don't pretend to even understand or know. But the bottom line is there was an instrument that was originally selected for Voyager that ran into development problems and budget issues and so on, and it was essentially thrown off the payload. NASA came back to Fred Scarf and Don Gurnett and said, present us with a proposal for a plasma wave instrument and work together on it. And so that's the origin of this instrument. You're looking at the electronics here in the gold box. It's about the size of a book and it weighs a couple of kilograms. I've got arrows there pointing to the PRA PWS antennas. PRA is a planetary radio astronomy instrument, and they were one of the originally selected instruments, and so we basically piggybacked on them. We share the signal from those antennas. Let's see. In part of this so-called shotgun marriage, Fred Scarf was named the original principal investigator for the investigation. And Don Gurnett led the development of the instrument here at the University of Iowa. And that's basically how I got involved as a graduate student. One of our engineers, Bob Shaw, well, he's a scientist, but he handed me an assignment. He said, here, write a telemetry document for this instrument that's going on Voyager. And so that's the first thing I did. I think I started working on that in 1974. And that's what got me involved. After writing some of the documentation, I helped test some of the electronics. I did the calibrations and wrote the calibration document for this. And all the while I was working on my PhD, and the timing was pretty good. I ended up defending my PhD thesis about a month before Voyager 1 got to Jupiter. And I asked if I could stick around to see what came back from Voyager, and I guess I'm still doing that. See, I don't know. Let me go through a couple of pictures. Well, let me say a little bit about what some of the results from the Voyager PWS investigation are, because I'm really not going to say very much about the science. I'm not going to show much data. But some of the highlights from my point of view is that we made the first detection of lightning on another planet. At the time Voyager flew past Jupiter, we knew lightning at Earth, but we didn't know any other planet supported lightning. And we detected lightning whistlers as we flew past Jupiter. I should be fair and say that the imaging instrument took pictures of the dark side of Jupiter and saw clouds that were lit from below. So I think the papers that came out in Nature or Science, I can't remember which, ended up being published simultaneously. So it was a simultaneous detection, but we think we knew what was going on before the imaging team did. Of course, being the first plasma wave instrument to travel to the outer planets, we were the first ones to look at what the plasma wave spectrum in the outer planet magnetospheres were. And I don't know if it should have been a surprise, but to me it was a surprise that we could see all the same types of plasma wave phenomenon at Jupiter and the outer planets that we do at Earth. So that's kind of reassuring, actually. As we flew past Saturn with Voyager 2, we actually crossed the ring plane just outside the main ring system that you can see in pictures and so on. And we were literally impacted by hundreds of grains of dust per second as we crossed the ring plane. And I believe that's the first time anybody had considered the possibility that an electric field instrument like the instrument we have on Voyager would be sensitive to dust. And these are micron-sized particles. They're about the size of the grains in cigarette smoke. When they hit a spacecraft with a relative velocity of 10 kilometers or more, they basically explode. And the gas that's produced is at a temperature of 100,000 degrees or so, and of course becomes immediately charged. And so some part of that process allows us to detect the electric field. And Allison is actually working on studying dust impacts all the way out to 160 astronomical units with this instrument, which makes them the largest, the most distant observations of interstellar dust that exists today. We study high Mach number shocks in the outer heliosphere. It turns out as you go farther out in the solar system, the plasma density drops off and the Mach numbers tend to go up. And so we've been able to study high Mach number shocks. Of course, the magnetized planets produce radio emissions, and we've studied the low frequency end of that. The planetary radio astronomy instrument studied the most of that spectrum. We started detecting radio emissions when the Voyagers were about 15 or 20 astronomical units from the sun. We detected them at frequencies of like 2 to 3 kilohertz. These radio emissions cannot be detected at the orbit of Earth because the solar wind plasma frequency is like 25 kilohertz, and radio emissions simply can't propagate below the plasma frequency. So we had to get far enough away from the sun before these became visible. And we scratched our heads for a decade, literally, trying to understand the nature of these radio emissions. And Don Gurnett finally figured it out with some help from Jim Van Allen. We had 2 radio storms that were separated by about a solar cycle. And Van Allen pointed out that each of these storms that we saw was preceded by something on the order of 400 days by the 2 largest forebush decreases that had ever been recorded on Earth. And so the idea was that solar transients propagate through the heliosphere. Eventually they get out to the heliopause, produce electron plasma oscillations, and those plasma oscillations can mode convert into the radio emissions that we were detecting deep inside the heliosphere. I think it's one of the amazing things is that when we realized what this process was, number one, it gave Don the ability to predict exactly, well, not exactly, roughly how far out the heliopause was using time of flight from these forebush decreases and when we started seeing these radio emissions. And it turned out to be something between about 115 and 160 astronomical units. And I think people who were paying for Voyager to get to the interstellar medium were probably disappointed that they were going to have to wait till we got out that far. I found it amazing that when we did get out to that region, not only did we cross into a region that we expected to see from the point of view of plasma density, but we actually measured these plasma oscillations that Don's theory predicted would be there. So it's kind of interesting to have a prediction and then find out 30 years later that your prediction was correct. Partly because of these plasma oscillations, we can measure the electron density in the interstellar medium. I'll show some data on that shortly. And the other surprising thing, I think, is that we have evidence that solar transients can propagate all the way through the heliosphere. They basically, some of the pressure that ends up reaching the heliopause is transmitted into the very local interstellar medium, and we have evidence for shocks that continue into that medium for tens of astronomical units.
Hey, Bill, there's a quick question from Fran in the chat. She wanted to get a reminder of how big the plasma wave antennas were.
Plasma wave antennas, well, they're made of beryllium copper, and they're 10 meters long. I think they're about 1/4 inch in diameter. And they're basically rolled up on a spool, and as the spool is fed out through some forming device, they've been heat treated to go back to their cylindrical shape. I should say that there's a little bit of thermal bending early in the flight, and the operators of the spacecraft were a little bit concerned that thermal bending was going to basically induce motion to the spacecraft, which was then going to blur the images from the imager. Turns out that by the time we got out to Jupiter, that wasn't a problem, but it's why we have these big, very large, very rigid antennas that were flown on Cassini, so that thermal bending wouldn't occur. Does that answer Fran's question?
I think so, yes.
Okay. I guess I wanted to pause a little bit and, well, let me go on to some of the pictures I have here. These are some people that well, some of you know these people, and some of these people are probably strangers to most of you. This black and white picture, a guy named Bob Shaw, he was a student of Don Gurnett's. I actually worked for him early on when I was an undergraduate student. Bob was basically the project manager for the project that built the Voyager instruments. Unfortunately, he passed away due to cancer before the mission was very far along. Then the four guys you see there are Don Gurnett in the blue shirt. Steve Remington was our lead electrical engineer. And then that's me. And then the guy on the right is Roger D. Anderson. And you might be curious as to why we called him Roger D. Anderson. And it's because some of you know another Roger Anderson from Iowa, and we had to separate the two. The other Roger Anderson, the scientist, was Roger R. Anderson. Let's see. So here's this picture on the left is one of my favorite pictures. I think we were probably this must have been one of the early encounters. I don't remember if it was Jupiter, Saturn, or Uranus, but starting from the top is Fred Scarf. As I said, he was the original principal investigator for the PWS. Then there's Don Gurnett. Fred passed away in 1988, and Don took over as PI until he passed away in 2022. And now I'm the Stuckey, I guess you could say.
Where was that picture taken?
That was at JPL.
Okay.
The color picture there, and Fran will remember some of this. I think the Jupiter and Saturn flybys, there seemed to be this is some politics that I wasn't privy to, but I think there was a pretty tight restriction on who could actually attend the flybys. You basically had to be a team member. But for the later flybys, it was agreed by the science steering group that guests could be invited, and you can see on the right picture there, that's James Van Allen helping us understand the plasma wave data. That's Don Gurnett to his right. Behind him is Eva Cairns, who was a postdoc here in the department at Iowa working on the Voyager data. Beside him in the blue shirt is Dave Barbosa. Dave spent most of his time at UCLA, but he came to Iowa for a few years and was a great colleague, a brilliant scientist actually. Worked on a lot of the Jupiter observations. And then finally, the guy on the far right is Larry Granroth. He's worked on data analysis on Voyager for almost as long as I can remember. I don't think he was quite on board at launch, but very soon after that.
He's still here.
Yes, he's still here. I should make a comment about Fred. As I said, I finished my PhD just before the first Jupiter encounter, and in those days we didn't have internet, so everybody showed up at the Jet Propulsion Lab, and we had these really crude outputs on thermal paper of what our data was looking like. And I remember being in one of our cubby holes at JPL with Fred looking at some of the recent data. And all throughout the lab, they had these little black and white 12-inch CRT screens. And every 48 seconds, a new image would show up. And so even though they were black and white, these were the highest resolution images that anybody had ever seen of Jupiter at the time. And Fred turned to me and he said, well, I really feel sorry for you, Bill. And he kind of caught me by surprise. I says, well, why on earth would that be? He says, because this is as good as it's going to get. You'll never experience anything like this again. And I don't think anybody, Fred included, myself included, realized that we would still be being amazed by the data that comes back from Voyager, literally 45 years after that time. So this is just one of the things that you experience early in your career, and you wonder, will it ever get better than this? And at least in my case, it did. Here's another picture on the left. Some of you may recognize Stan Shahan. Stan was a professor here at Iowa. He left Iowa and went to headquarters and was one of the earlier division directors for what's now called heliophysics. At the time, I think it was called space physics. And he was responsible for getting GGS and missions like Polar and Equator and so on going. Then there's Fred Scarf. Sitting in the white jacket is Charlie Kinnell. He was well, he still is a giant, but he was a giant in our field to start with. He spent a lot of time at UCLA and went to Scripps, and he was actually an associate administrator at NASA for a while. And then sitting beside him with less hair is Ferd Cornady. Charlie and Ferd were consultants at TRW for Fred Scarf during the Voyager days, and they worked on some of the early observations of Chorus by Voyager in the radiation belts of Jupiter. And then in the right picture, standing beside Don is Alex Dessler. He was not directly, I don't think he was actually a team member on Voyager, but he was certainly an influential member of the community. He hosted an early Magnetospheres, the Outer Planets meeting at Rice University, and was really a leader in the field of planetary magnetospheres. We always laugh at this picture because we can't remember what Don was explaining in this picture, but we think it had something to do with how butterflies fly. And I guess I probably shouldn't even show this, but there's a number of people I work with that have never seen me without a beard. So on the left, that's during one of the Saturn flybys. And on the extreme left is Chris Russell from UCLA. And then, of course, Fred Scarf. And then the picture on the right is me with my little brother and my oldest son. And I'm only showing this because this is my favorite Voyager t-shirt, and it's a really poor picture. Some of you old people, Fran, I'm talking about you, might remember this. It's basically a picture of Voyager with a pirate sitting on the end of the scan platform, and musical notes coming out of Voyager, because Fred, in some of the earlier press conferences at Jupiter, for example, found ways of, well, we actually produced sounds from the waveform measurements from the PWS instrument. We had sounds of whistlers and the bow shock and things like that that Fred would play at the press conferences, because it was really hard to get the attention of the press corps after Brad Smith got up and showed all these amazing pictures of Jupiter and its moons and the other planets. So the musical tones that came out of the instrument ended up in this t-shirt. So I kind of like that. Okay, so this is basically one data slide that I wanted to show. The bottom panel is what we call a frequency time spectrogram. This is frequency on the vertical axis, and it goes from just under 2 kilohertz to 4 kilohertz. The time scale runs from 2012 out to almost near the present. And basically, the warmer colors indicate more intense emissions. These red splotches here are electron plasma oscillations, and they're way over saturated in this spectrogram, because I tried to get this little thin line to show up at the same time. But these are the electron plasma oscillations that we detected after crossing the heliopause, which occurred in August of 2012. And even though the frequency resolution doesn't appear in this supersaturated display, we can look at the frequency of these emissions. The electron plasma frequency is directly related to the electron density, and we can calculate the density. We saw about 8 of these events as we went farther and farther out into the interstellar medium. I should say these broadband emissions are not really emissions. They're evidence of noise in the telemetry from Voyager. You know, Voyager's out beyond 165 astronomical units now. It's over 23 light hours away. And it's very hard to get a signal back from the spacecraft. I'll show you some pictures of how that's being done now. But these regions where we have a lot of apparently low frequency noise, that's just bit errors in the telemetry from the spacecraft. And the gaps that you see, that happens. These more recent ones have to do with issues that you've probably read about in the news, with Voyager having issues that had to be corrected from, well, a light day away by the miracle workers at the Jet Propulsion Lab. But we're still getting some of this data. This most recent bit of data here came back in late April. And as I said, you can take the frequency of the plasma oscillations and this narrow line that we've identified as a quasi-thermal noise emission. That tells us the plasma frequency also. So then we can plot the electron density as a function of time, and that's basically distance. And it's very clear that we have a radial gradient in the electron density as the spacecraft left the heliopause. This type of data from Voyager 2 is no longer available. That part of that receiver is no longer returning usable data. We do have a lower resolution spectral measurement from Voyager 2, and we have a few measurements of these plasma oscillations from Voyager 2 that reflect exactly the same type of radial gradient, even though the 2 spacecraft left the heliosphere in greatly different directions. that's what we spend our time working on these days. And this is how we get the signal back. This is the deep space complex, the Deep Space Network complex at Madrid. There's also one of these in Goldstone, California, and near Canberra, Australia. And you'll notice that the 70-meter dish and 4 of these 34-meter dishes are all looking the same way. They happen to be tracking Voyager 1 at the time, and this is what it takes to get 1.4 kilobits per second back from Voyager 1. Some of the older ones of you in the audience might remember 1200 baud modems. Well, that's about the maximum that we can get back from Voyager 1 these days. I should say the normal data rate that has what some of you might call survey low rate data comes back at 160 bits per second. And that typically takes either a 70-meter dish or a couple of these 34-meter dishes to obtain those signals. This has happened a couple of times. Here's a nice nighttime picture. This is also in Madrid of 5 of these dishes looking at Voyager 1. Actually, I think there might have been 6 for this one. And this is the most recent tracking in late April of this year. And it turns out at the same time that these were tracking Voyager 1, we actually, some of the data that you saw on the previous slide came from this particular track. They were also tracking with the Green Bank telescope. This is a 100-meter telescope in West Virginia. And this is the Effelsberg 100-meter dish in Germany. These were kind of experiments to see if they could track Voyager 1, even using 5 dishes at the Deep Space Network. We're just barely above the signal to noise ratio we need to get good data back for these higher data rate periods. So I don't know if the plan is to try to use one or the other of these or to gang them up with the Deep Space Network or not. And I don't think there's been any agreements to do this yet, but it was basically an experiment to see if it could work. We'll point out that at Neptune, they enlisted the VLA to get higher rate signals back from the Neptune flyby. Allison.
Thanks, Bill. Yeah, so I wanted to transition just a bit to talk about what my experience has been on this project, but also in general in science. And Bill and I were chatting about, what we were going to talk about on this webinar today last week, or no, it was a few weeks ago. But I had mentioned this idea of talking about imposter syndrome, and Bill was like, "Yeah, I can say a few things about that too." So we thought it might be nice to show this intergenerational link between, among what we both feel is one of the strongest barriers to sometimes building up confidence and doing really well at your job, and that's this imposter syndrome. I'm showing this graphic from a Lego grad student, which is one of the best representations that I've seen of some of these barriers. But the idea behind this is just that we are working with very, very smart people, right? We are smart people, but we're surrounded by other very, very smart people. And there's so much to understand about the universe that we just will never know all of it. So we're constantly confronted with things that we don't know, which makes it difficult to then in your head tell yourself that you're smart enough and you belong and you're welcome in this community. And it makes it maybe a little bit harder when you then add on the different layers of the identities that certain people have. For example, myself as a woman, and then looking at all the pictures that Bill was showing of the early Voyager days and the early days at University of Iowa, I don't see anybody like myself in those pictures. So that can add just an extra charge to this type of feeling. And I know that other people with other identities feel the same way. And I think a lot of that's changing these days slowly, and kind of we're uphill battling our way through that. But it still contributes to this overall feeling of, what if I'm not good enough and what if I don't belong? So I feel that way all the time. It's not crippling. It's not a crippling feeling, but I have moments of it kind of constantly. And I think Bill can say a little bit about what he feels too.
Every day, especially when your students come and ask me questions that I can't answer.
Yeah, yeah. It's difficult, and I don't think I've ever really known anyone that I've worked with or in this field that hasn't felt this way at times, if not every day. So I think that's important to normalize and talk about with our students and with people that are entering into this field. And it's difficult, but we can make it a little bit better, I think. And so I'm going to also share one of the ways in which I have gotten better with dealing with these types of feelings. And that is by engaging in lots of activities that make me feel more connected and more empowered in my community. So I'm just showing an example of some of the stuff there that I've been working with since I came to Iowa and became a professor here. And this whatever this group of things might be for you might be different than what it is for me. But there are lots of ways in which you can engage in activism and empowering activities that allow you to feel more safe and secure in your own self, and that translates into your work, right? So if you can get to be more resilient with your own character, and when you go to do your science work, all of a sudden you have way more energy to do it, you feel more confident, and it just kind of changes things quite a lot. So I wanted to throw this out there as one of the ways in which at least I can combat that imposter syndrome. And I don't know, Bill, if you have any other suggestions on how you get around it.
Not really. As I said, every day I run into it. So
Yeah.
there's things that I don't know, and I think there's things that I'm reasonably good at, but I always run into people, even in my own group, that understand things better than I do, and I rely on them to help me.
Yeah, well, that's half the reason I love having students so much is that they teach me things that I don't know myself until they tell me, and it's an amazing experience.
I think that might be the end of it here from our presentation. So, Nick, if you have more questions from the audience or whatever, we'll try to answer them.
Great, thank you so much. That was really useful and valuable, and I appreciated all of it. So I don't see. So please feel free to you can either put questions in the chat, or you should have the power to unmute yourself. If you don't have the power to unmute yourself, I'll unmute you. So I have one question that popped up for me. It was I didn't realize that Voyager had gone through the ring plane of Saturn. And I know you said it was outside the major belts, but what was there any like risk concerns?
Um, Yes, I mean, there were concerns. I vaguely remember there was a long discussion, and Fran may remember more about this than I do, about using Pioneer 11 as a pathfinder. There was a question about whether we could go between the rings and the atmosphere at Jupiter, at Saturn, which actually Cassini has done now, but I don't think Pioneer 11 did that. We crossed outside of what I think is the G ring with Voyager 2. Could be wrong, but we were actually in the E ring, which people didn't really recognize as what it really is. It's the dust and gas that comes out of the Enceladus plumes at the time, but the entire system at Saturn is filled with both neutral gas and dust. And the cosmic dust analyzer on Cassini did a great job of analyzing that. But yeah, we flew through the ring plane outside of the main ring system. I will say that one day when we were at the assembly facility at JPL, they called it SAF, we were trying to do a test with the PWS, and there were guys out on the scaffolds around the spacecraft banging around. And every once in a while, I could see a wiggle in our data when somebody did something to the spacecraft. And for totally incorrect reasons, I thought, you know, when we go through the ring plane at Saturn, we ought to be taking data to see if we see any effects of the kind of the mechanical interaction with dust. And as it turns out, it's not. It's an electrical interaction that we detected. But we just happened to have high rate observations at that point in time that we could analyze. And it was the first time that we'd used electric field instruments to say anything about dust in a planetary system. I should say that the planetary radio astronomy experiment saw similar signals and had similar interpretations.
So Nick unmuted me because I think he wanted me to comment. And you asked me, Bill, whether I had any recollection about the pioneers and voyagers avoiding the ring plane and so on. I'll be honest with you that when Voyager got to Saturn, I had just finished up my PhD and I was preparing to head off down to Peru to go on a climbing trip. And I didn't pay a lot of attention to the Saturn stuff. I was involved with the papers and a bit of the analysis, and I was there for the encounter. But I was not paying, I wasn't hugely involved. I got distracted with finishing up my thesis on Voyager going through the EO Taurus. So my question for each of you is, what do you think is what was the most surprising, thrilling, exciting result that you got from the PWS experiment at Voyager?
Well, before I answer that, I should let Allison answer. But first of all, I wanted to point out to Allison that here's an example.
Mm-hmm.
Fran has been on Voyager for years and years and years, and she's female.
Yes. Well,
yeah, but pretty rare, to be honest with you.
Yes.
So very often I was the only woman in the room.
And you have been, Fran, you've been a significant just mentor, even for people who don't even know you, who've never talked to you. You have been that for so many, many people just by being in that room.
Well, it helps to be feisty.
I think for me, I still, of course, I wasn't really working on the project at the time. I've only been on this project now for a few years, but the results that really stick out to me are the transients, the solar wind transients coming from our sun that we could see out in interplanetary space in the local interstellar medium. And Bill mentioned this being able to sonify these wave spectrograms so that people can listen to what these things sound like, whistlers at Jupiter and other things. But you can listen to that transition through the heliopause and beyond, and then hear those shocks hit at those intermittent times. And I always play that for people when I'm talking about Voyager in these public talks, outreach talks. And it's impressive. It's like people's faces just kind of like go into this shock mode, just hearing the sounds of that, because they don't know all the details of the science and the physics, but I think it's still really curious that we can see those so well. And we're now, of course, projecting out when we would see something like the Gannon storm that happened in May of last year, when those will reach the Voyager, and we've had discussions about that in our SSG meetings, and super fascinating to think about. If we still have data, we'll be able to see those come out and hit Voyagers.
Yeah, I vaguely remember getting a side comment from the magnetometer principal investigator after one of the press conferences. Fred had played one of these sounds. I think it was Saturn, and so you have Brad Smith showing all these great pictures of Saturn and its moons and rings and so on, and then Fred gets up and plays these sounds that they don't quite make the same impact as some of the images did, but people's eyes light up, and they can kind of relate to the sound even though they don't understand the physics necessarily. And I think Norm Ness made some comment about he's showing wiggly lines, what's the magnetic field look like? And those of us who do magnetospheric physics are always accused of doing wiggly line science, and nobody can understand. And made some comment about smelling our way to the next planet. So,
Cool.
So
I'd like to
what's
point.
your
Sorry.
yeah, what's your biggest coolest result?
well, I think this whole story of detecting these radio emissions back in 1983, scratching our heads about where they came from and why they're there, and finally coming up with a model that says, okay, they come from plasma oscillations beyond the heliopause. Flying through that region and actually seeing those plasma oscillations. I think I can remember the night when we first saw those. I used to go home at night and look at the most recent data from Voyager, and we saw this in our low rate data long before the waveforms had come back from the recorder, and plotted out the data, and I said, that's them. It took less than 10 seconds to figure it out. I made some plots, brought them into work, showed them to Don. He says, plasma oscillations. I mean, it was instant, well, it was gratification that took 30 years, but it was instantly recognized as to what it was.
Impressive. I'd just like to point out that talking of pioneers and inspirers, we have Marcia Neugebauer and Margie Kivelson both on this call. And of course, they are the pioneers of our field and phenomenal women, mentors and inspirations. But thank you both for your history that you've just presented, Bill and Allison. Thank you.
It's always fun talking about Voyager. So,
David put some appreciation in the chat, so you might want to read that. I got a quick question for Allison. I'm just thinking about the story you told at the beginning, and then your comments on imposter syndrome and recharging. Can you say a little bit more about like the importance of I mean, what struck me about the story was you took the time after a conference to take some time, right? To and recharge or decompress. And I don't know if you want to say a little bit more about that importance of that. I think there's some challenges that we have in the community about that.
Yes, I mean, one of the other features of our jobs is that there's no like end goal or end date with our work, right? We can work forever and we'll never be done. So that can sort of snowball quickly into you're working all the time and you're never done. But we kind of have to make peace with the fact that we're going to hopefully get old and then die, and not have done everything that we could have hoped to do in this life in terms of our science accomplishments. And so part of that is, taking the time to enjoy things along the way. And we have these jobs that allow us to travel across the world and to meet people, and not just colleagues, but the people who live in these places that are very different from our own. And it's really worth taking the time to immerse yourself in those places, meet those people, and have those human connection experiences that you're able to do because a lot of this is facilitated by the type of work that we're involved in.
Great, thank you. Any last questions or comments for Bill or Allison? We're closing in on the top of the hour. Great. Thank the two of you so much. Really appreciated this. I just wanted to pop up this one last just reminder of some of the upcoming events and where you can find Shield on the web. If you've got any suggestions for future activities or talks, we're making plans for the fall, but we're not, it's not full yet. So please feel free to reach out. All right. Let's thank our speakers again. If you haven't done so electronically, and then and we'll call this one to an end. Thank you so much.